Thank you. It gets better, right? Okay, so first stage, input stage, and it was a diff pair. We did that last time, so I'll just kind of draw that out. And if it doesn't go all the way from ground to the supply, then you haven't gotten the complete stage. And notice here's the supply, and here's ground, and it goes all the way from the top to the bottom. So that's very possibly a complete stage. What did we say about Q1 and Q2? Why are they there? What are they called, and why are they there?
Darlington pair, and they have high input resistance.
Yes, so you have that on both sides. And then this right here, this is not a current mirror. This is just a way to set the base voltage on Q9. And I think I only got, did we go through why this increases gain, or was it just the other section?
I think that was in lab.
Okay, right. And then why did it have a low current? Over here we've got 100 microamps, but right here we have just 6 microamps. Why is that?
That increases the input resistance, right?
Increases the input resistance. So there's R pi in the input resistance equation, and what's the equation for R pi?
Oh shoot, I'm not muted again. I do have a question. Sorry.
Okay.
For the why isn't Q8 and Q9 a current mirror?
That right there, it's a biasing technique, but if it was a current mirror, Q8 would have a resistor above it, and it wouldn't be part of the circuit. It would be a separate circuit that generates a voltage.
Okay, thanks.
Okay. Yeah, so R pi is in the Rn equation, and what's the equation for R pi?
Is it beta times VT over IC?
Yes, and if you use a small IC, what happens to R pi?
It gets larger.
Gets larger. So that's what's going on there. And if we have time, we'll talk about this. I wanted to get to capacitance before the end of the class, so we may come back to that. Does anybody know what these diodes are doing? Think of 347 first lab.
Is it protection?
It's protection. Usually, which end of the diode points to the lower voltage? Is it the one with the line, or the top of the triangle?
The line.
The line. But look at these. Is the line side going to the lower voltage?
No.
No. So why are they there? How do they
protect
work?
Against current going the other way?
Okay.
So is
okay.
it so like if the input voltage rises above VCC or below ground, that it'll shunt the current to ground or VCC instead of like back powering things?
Exactly. So if the non-inverting input goes 0.7 below ground, then the bottom diode will turn on. The top one will still be off, but the bottom one will be on, and it'll clamp it. It won't let it go too low, and it also gives a place for current to run. You know, when you touch your hair, you pull electrons off of it, and now you're depleted of electrons. If you touch something that has a lot of electrons, those electrons will flow onto you. And if that thing that you touch happens to be a chip, then that current will come out of those pins. If you have too many electrons and you touch your chip, then the electrons will flow into the chip. That's electrostatic discharge. Okay. And then this one, it's also upside down. So when does it turn on? What do you think?
The input's 0.7 volts higher than VCC.
Exactly. So if the input's too high now, it will clamp it. It won't let it go much higher than the supply voltage. Okay. All right. So let's call this check. But at some point. If not today, I'll come back and talk about this. Okay, what's the next stage you found? And let's ignore the capacitor for right now. What's the next stage you found? So where's the output of the diff pair going to? Which transistor?
Q10.
Q10. Okay. So what kind of amplifier? What kind of amplifier is Q10 part of?
Common collector.
Common collector. So this thing up here, again, it's a current source. That just means that you have like a constant current. It's probably a current mirror here. It could be a big resistor, but in this case, they decided to use a current mirror. So you have to circle all the way from the supply, all the way down to ground. And if you look at this, the input goes to the base, the output, if you look at all the wires coming out of this, there's really only one. This is kind of going through, but there's only one really going out. So you can see that's on the emitter. So it's not a common emitter because the output's on the emitter. It's not a common base because the input's on the base. What's left? The collector is a common collector. Okay. And why do you use common collectors?
Isn't it so you don't load like other stages in the in the amplifier?
Perfect, yeah. And so it's to protect your diff pair from being loaded by whatever comes after it. So let's look at what's coming after it. If we go to blue, okay. What's the next stage you see? What's it made up of? Let's even go friendlier. Where's the output of that common collector that we just circled? What transistor does the output go to?
Q11?
Q11, okay. So the question is, what kind of amplifier is Q11 a part of?
Also a common collector.
Also a common collector. What in this case got, I just crossed out the 100 micrograms. Oh. But wait a minute, you just had a common collector. Now you have another common collector? Why is that? What's going on there?
The first common collector acts as a level shifter as well, and it level shifts up. So I assume the second one's there to shift it back to where it's supposed to be.
Yes. Okay. So first level shifter, common collector, common emitter, level shifter, shifted the voltage up. But whoever designed this wanted the voltage to be, whatever voltage it was actually coming out of the diff pair. So it had to shift it back down. And that's what the second common collector is. Okay. The first one has a current source up top. The second one has a resistor. Which one do you think is going to have a higher R in?
The first one?
The first one, yeah. Let's see. What is the R in? Now remember that this current source is a current mirror, so the actual circuit would be there's your current, and then it would have its biasing circuitry over here. This would be diode connected. So this would be this current source right here. So this node right here is this node right here. So what is the R in of that first common collector, the orange one?
Very big.
Very big. Okay. What's the equation? You're
The
coming.
symbol, like the change in V in over change 9.
You can get even more information from that. What did you have when you had what was the Rn of? You can tell I don't have my pen. What was the Rn of that? See if the pen works. Pen's working. What was the Rn of that?
R pi plus RE times 1 plus beta.
Pi plus Re is 1 plus beta. And if you notice, if you come out the emitter here and you look down, you see a resistance of Re. That's what goes in there, whatever's below the emitter. So thank you. Good. Okay. So for this one, what's the resistance below the emitter? Let's ignore Q11 for now. What's the resistance you see below the emitter? If you go all the way up here and hit this thing, what's the resistance you see there? Looking up into here. So you're hitting a collector of a transistor. What's the resistance? RO. Okay. So if you try to see what the resistance is looking up into the circuit, this circuit is actually this current mirror, and this current mirror, if you look into this terminal right here, you hit a collector, and that is RO. So back to the quick method again. So the R in here, coming in Q10. So what's the RN resistance that you see? It's a flipped circuit, but it's still a common collector. So you still look under the emitter for the resistance. In this case, it would be above the emitter. What do you think?
Is it like R pi plus RO times 1 plus beta?
Exactly. R pi Q10 plus, and whatever resistance is connected to the emitter, that's RO times 1 plus beta. So that's gigantic. What's the Rn of this one?
Just the standard RN with RE instead.
Yep. R pi Q11 plus whatever this resistor is here. 1 plus beta. And you are pretty much guaranteed that RO is much bigger than R. So the Rn here is really big, so it's not going to load this at all. But now you can get the shift up, shift back down, and now you're back to the same voltage that you had out of your diff pair. Okay. All right, we're through 2 stages now. What's the next stage you see? Or what's the next amplifier you see?
Common emitter on Q12.
Common emitter on Q12. What color is good? Red? Okay. So Q12 is a common emitter, and you have to go all the way down to ground, all the way up to the supply. And this is written as a current mirror. What's another, what flavor of common emitter amplifier is that?
Active load?
Active load, yes. So this is, when you see a current mirror up top, that just means you have a PNP up there, that's what an active load is. So this is a common emitter with an active load. Okay, and if you had to name a stage, what stage would that be?
Gain stage?
Gain stage. So we finally have a gain stage. So we've got input stage and then some muckety muck and then a gain stage. Okay. Any other? What's next? What's your next stage? Oh, pen stopped working again. Okay, we'll make it. What's a good color? Purple.
Purple.
Okay. So what? Last stage, probably an output stage. So what transistors make up the output stage? Not any safety circuitry or anything else. What transistors make up your output stage? Transistors, resistors, current sources, whatever.
Or that just be Q5, Q6, and Q13, right?
Yes. Yes. Q5, Q6, Q13. You have to go all the way down to the bottom, or it's not a complete stage. And what kind of output stage is that?
Push-pull.
It's a push-pull. And what's different about it than the push-pulls that you've seen? You've already seen the the NPN, the PNP.
It's got a Darlington pair on top.
Yeah. Why would you use a Darlington pair in an output stage?
So you can source more current.
Exactly. Yes. So if there's something out here that you connect this to that needs a lot of current, this thing says, no problem. I have a Darlington pair. Okay. Again, a lot of these schematics are kind of not everything's drawn in. Does this have crossover distortion? Okay. What is crossover distortion again? What does crossover distortion look like? So let's just draw that out. Remember in lab where you saw something like this? That's crossover distortion. Disto. Okay, so is this circuit, as it's drawn, is it going to have crossover distortion?
Yes.
Yes. Why is that?
You have a drop of 2 VBE for the top pair and a drop of 1 for the bottom, so there should be a gap in the middle where both are not conducting.
Or both are conducting. That one point.
Yeah.
Okay. So you need 3 VB on between the base of Q5 and the base of Q13. How many VB on between those 2 points? In actuality. So just exactly as you said, that was perfect. So inside this purple circle, if you travel from the base of Q5 to the base of Q13, you have 1 VB on drop, 2 VB on drops, ignoring the resistor, 3 VB on drops. So you need 3 VB on between those two. Something has to set those voltages so that whatever's setting the base voltage here and setting the base voltage here, they need to be 3 VB on apart, or else you'll get crossover distortion. So what's the voltage difference between the base of Q5 and the base of Q13?
Oh, it's 0. They're tied together, right?
Yes.
And therein the problem lies.
Yes, exactly. So this one, again, like I said, some of these schematics are cleaned up, but this one is definitely as drawn, will have crossover distortion. If you were using diodes that had a magic perfect VB on voltage, where might you put them to get rid of the crossover distortion?
You could throw them in between those two bases, right?
Yeah, just
That
some-
delays the turn on of the other pair until you're past that voltage.
yeah, just somewhere. I'm not sure whether it's better to go above here. I don't think it matters. I don't think it matters. If when you're working, you actually build this circuit and the diodes don't go here, don't come back and get mad at me. Okay, yeah, so like 3 diodes there. Now we've got 3 VB on between the 2 bases, and we've got rid of the crossover distortion. Okay. Let's see. Are there any? Oh, let's do one more. I need one more color, but I think I'm out of pretty colors. Should we go? Pink is kind of near purple. Weird green. So here's something. Does anybody remember what that's doing? And I have it on my list here that I was supposed to look up about why
It's current limiting, right?
it's current limiting. And how does it work again?
When there's a drop across RSC because you have a lot of current in the output, it biases Q7, which pulls base current away from that Darlington pair on the top.
Yeah, it turns on Q7. Current goes through, instead of going into the base of Q5, it comes down and goes out here. And this one, it has this extra outlet right here. So it doesn't all go out the output on this one. The last one, it all went out the output, according to the schematic. Okay, so I didn't quite get to explaining this, and I didn't answer the question on exactly on this current. Those will both be on my list for. I mean, I could throw together a video. Would that make people angry, or or do you want me to do it in class?
The video is good.
Okay, so I'll put that on my homework. But otherwise, this is a pretty fancy amplifier, and all the parts are there, and you know how to build all of them now. Okay, I have 8 minutes. How about this? I'm gonna go through this part of the amplifier. I know some of you heard it already in lab, but this is another interesting thing that you'll see. I know some of you maybe used the LM13700 last week or this week in lab. It actually uses the same kind of technique to increase its gain a lot. So I can't really, how about in chat? Where's chat? There it is. Okay, in chat, if you've already heard the explanation of this, can you just like type something random? Nope, nobody? Okay, and then let's talk about this bottom part right here and how it works. Okay, so let's see if the pen's back. Nope. Okay, so let's do an NPN just because they're easier to see. We'll look at the LM13700 in here too before the end of the quarter. Sorry for being so slow here. Now when you diode connect this, it makes it so this output over here is not usable anymore. So it means that you can't use this as a differential output circuit anymore. Okay, so let's go step by step here. Let's assume a balanced input, which means if I put a plus delta V here, this is a minus delta V. So one side goes up, the other side goes down. Let's say we do that. What happens to the current through the left side, through VI plus?
Goes up.
Goes up. So before this, if we started with VI plus equal to VI minus, then we had ISS over 2 through both sides. I want my pen to work. It's working again. So weird. Okay, so you had ISS over 2, but now since you changed the voltage, this gets some extra current, and this side gets a little bit less current by the same amount. Okay, so this Q1 has turned up its current, and any current going through Q1 is also going through, shall we call this Q3, Q4, Q2. So any extra current is now going through Q3. And Q3 says, okay, I have more current through me. I have to accommodate that current. What's going to happen to VBE or VEB?
It'll increase?
It'll increase. So this voltage right here, let's change colors. This is actually VEB. But yeah, it's going to increase because you just turned up the current through that side. That PNP says I have to accommodate more current. It increases its VBE. The thing is that Q4 just uses whatever base voltage Q3 generates. So Q3 just said, I had more current coming through me, so I have to increase my VBE, and it takes the base voltage and drops it a little bit, so its VBE will increase, or VEB will increase. That actually also increased the VBE on the right side. So VEB Q3 increases, and since the VEB of Q4 equals the VEB of Q3, VEB of Q4 also increases. Okay, so let's stop that. That's one story. We have another story going on what's happening over here. So because you dropped the voltage of VI minus, what happens to the current here again?
That current drops.
This current drops. So now whatever current's going through Q2 also has to go through Q4. So the current through Q2 dropped. That means the current through Q4 dropped. And now let's look at the last piece of this. You have the two pieces of the story, and then there's your current equation. Now for Q4, what happened to its IC? What happened to Q4's IC?
Decrease.
Decrease. This decreased. So let me move this down just a touch. We're almost to the. Okay. What happened to its VBE?
Increase.
VBE increased. So this increased. That's the exact opposite direction it should go for IC to decrease, right? Okay. But Q2 decides the current through that side. So the current has to drop, but VBE increased. So how is this transistor, how is Q4 going to drop its current back down so it equals that new ISS over 2 minus delta I? What other knobs does it have that it can turn?
VCE drops by a ton.
VCE drops by a ton. So to make up for VBE increasing and IC decreasing, drops by a ton. So by changing VB in the opposite direction that the current changes in, VCE has to change a lot. It has to make up for VBE, which is in the exponent, which is changing the current a whole bunch. It has to fight that. Plus it has to turn down the current even more than how much VBE is changing the current. So this actually, by doing this connection right here, it actually increases your gain, and it lets you get rid of the biasing circuit. But this only works if you just need one output. If you need a differential output, you can't use this. Okay, it's a touchy-feely practice again. Any questions on that? All right, then I'll get the capacitor stuff to you somehow. Anyways, I wanted to make videos for that stuff anyway. Okay. Then by Wednesday, try to watch the video and we'll do problems in class. We'll kind of flip Wednesday. Okay. Any other questions? Okay, that's all I got.
Thank you, Tina. Have a good week.
All right, thank you.
Thank you, Professor.
Yes, have a good weekend.
Thank you.
Sleep, please.
I think, yeah, absolutely, I will. Hey y'all. And it's 10 after. Yay. Okay. This week, like I said, it's not a valid excuse because that means I'm not doing my job, but I still don't have the midterm posted. I made progress on it this morning, and there's not too much left of it, but I may fall asleep, but I'll get it posted today. And then I'll give you a week, so next Friday or something, or Saturday if you need it. And then we have a whole week to talk about it. A whole week to set up meetings. I know you have projects due and all that, but hopefully you'll have time to look at it. Anything else that I need to do? Oh yeah. Okay. So today my goal was to talk about capacitance, but we spent the whole time on going through another amplifier, which I think it's really valuable. I think it's good stuff. So I don't mind. I don't think that's wasted time. It's just that next week I think you'll be talking about frequency response in lab, and I was hoping to get that information to you. But since I didn't in the first class, I'll you all, somehow we always get done with 20 minutes to spare. So I'll probably be able to talk about it during the hour, but I'll also make a video and post it. so you have that information for lab. Okay, and I can't think of anything else business-wise. Okay, so what I'd like to do is just let you loose on this second amplifier, and to find this, what just happened? There we go. In week 7, there's this more sample amps. So it's that same document we looked at on Wednesday. And the second amplifier, that's week 7, last handout in week 7, is this one, figure 2 schematic diagram 104 LM 124. And I'd like you to go through and circle every stage and decide what kind of stage it is, what kind of amplifier and what kind of stage it is, and then see if maybe the current is doing something that's special, or if there's something you notice about one of those stages. So pretty much just doing the, what's it called when you have a sentence and you map out what's a verb and things? Forget what that's called. But doing that to the amplifier. And I'll turn my voice off so you can talk, or I could throw you in a breakout room if you'd like to do that instead. What's the vote? Breakout room or main room?
Let's just stay here, honestly.
Okay. I'll mute myself and let you add it. I think so. I'll make it so you can share the screen if you want to do that. Is that good? Okay. Okay, all yours.
Okay, so we know that the first stage is a diff pair input because we went through this in class last time already, the beginning of it. But so it looks like for the output stage, Q5, Q6, Q7, and Q13 make a push-pull output similar to what we saw in the last example. Does anyone agree or disagree with that?
I agree. Yeah, it looks like that.
Would we consider all 4 of them to be the push-pull, or would we only consider Q, 6, and 13, do you think? Or maybe it's not even.
Q6 and Q13 would be the push pull, and the other 2 are for safety, aren't they?
That's what I'm thinking.
Do you mind if I interject? What's if somebody just pulled Q5 and Q6 out and asked you about them, what would you say?
It looks like it's a Darlington pair, maybe.
Yeah.
Oh, so maybe Q5 and Q6 are some sort of biasing for Q7 and Q13.
Tina? I noticed that I had to miss my sections class because I needed to turn in an application during the class period.
Okay.
But I'm able to join in now. Sorry for being late. But what are we doing?
Go to week 7. And it's the same handout as Wednesday. It's I think it's called More. What is it called? Even though we haven't done any yet, it's called More
Amplifiers, spring, something like that.
More Sample Amps, yeah.
Yeah. Okay.
And then we're looking at the second one and trying to circle each stage and
Okay.
and then decide what kind of amplifier each stage is.
Thank you. More sample amps. Dope. Are we on figure 2?
Yes, figure
Yeah.
2, LM124.
Got it. Cool.
And I'm just sitting back and being a bug on the wall.
Sounds good.
So I'm thinking since Q6 and Q5 are a Darlington pair, and it looks like the output is connected to Q7 and Q13, maybe. So
Casey, have you already mentioned like whether or not have you ever already gone over the input? Is that why you're
well,
going?
we went over the input stage last time in class, but we can go over that one.
Okay.
Or I can explain it if you'd like as well.
Yeah, could I try pointing out which one's the input first?
Yeah.
So I'm thinking the two Darlington pairs where the inverting and non-inverting inputs are a part of the input, and then Q8 and Q9.
Yeah.
As I guess they're I guess that's a bias setup to where there's an increase in gain.
Yeah.
Because of what was gone over in. I mean, Tina explained last homework that's done to increase the gain because a bias setup like that causes a larger change in that collector node with any given change in current with the two transistors caused by any change in voltage from the inputs. But are those diodes right there also a part of?
I think we're ignoring the diodes.
So this time, since we're there, so I agree on your input stage, but why are those diodes there? Think 347 first lab.
That was so long ago. Maybe they're for VB on. It gets you the voltage for the VB on for the transistors. I don't know.
So on a diode, the line, so there's the triangle, and then on the pointy end of the triangle, there's a line. Does the line go to the lower voltage or the higher voltage usually?
It's the lower voltage.
But here,
I'm wondering if those diodes, because since we're going from VCC to ground, we need to bias. I think we need to bias it at VCC over 2. So I'm wondering if the diode would help us, or maybe biasing is not the right word, but help us sit at that middle spot or something.
but which way are they pointing?
They're pointing away from ground.
Yeah.
Right?
So why might that be?
You want a would you want a negative potential at that node for some reason? Negative because I mean, if it's ground, right, and then there's the drop, it'd be negative 0.7 theoretically if that's the VB on.
Yeah.
Then there would be another. Wow, and then with that other diode on top, there would be another negative. So it would be negative 1.4 at VCC, which doesn't make sense.
Are those on in usual operation? If the non-inverting input is in between VCC and ground, are either of those diodes on?
No. Maybe it's like some sort of protection if your non-inverting input goes too high, so it can't rise above VCC. Or okay.
Do you remember the word clamping a voltage?
Yeah.
Yeah.
So if for some reason, like when you mess with your hair, you pull electrons off of it and you become positively charged. And if you touch something, electrons will rush onto you. Or if you have too much charge on you and you touch something, electrons will rush off of you. So those are for electrostatic discharge. If you touch that non-inverting input, then, and the voltage tries to go above VCC, this will clamp it at VCC plus the on voltage for the diode. Or if it makes it go below ground, it'll clamp it as the on voltage below ground. So that's just there for protection. And I had somebody in 348, maybe it was last year or something, they were building this circuit and they blew up their transistors. So they just grabbed the transistors from 347, and the 347 transistors have these protection diodes in it. And they couldn't get their amplifier working. It just didn't work. And it was because these diodes were turning on. So you have to be careful when you buy a chip. And it doesn't have this protection if you're trying to do random things. Okay, but this time do ignore the capacitance. Right? So I think I think you got the first stage good.
I think it's also sorry. I was going to say, I think it's also good to mention that the Darlington pairs are there in order to increase the RN even more of your input stage.
Oh yeah, I remember that part was gone over last period.
Okay, perfect.
Yeah, appreciate it though. But the capacitance that we're ignoring, is it the actual capacitor that we see right there? That's what's being ignored.
Yeah.
Yes, it's actually what I was planning on talking about today. But yeah, it's for frequency response. When you hook something up with feedback, you know, the oscillations you're getting with the analog discovery, that could very well be that there's an amplifier in there that's not, this is called compensation. But we'll get to that on Monday. Not Monday. Monday's a holiday. And some videos that I'll post. And I asked people to watch the videos before Wednesday, and then we'll just do problems in class.
Okay. Sounds good.
Okay, so first stage, check.
Okay, and then Q10 and Q11. Well, it looks like those are both common collectors. It's just PNP and NPN.
Yeah.
Two separate ones. So from what I gathered from last class, that there may have been some loading issues. And that's what the common collector transistors here are being used, amplifiers here are being used for to help with.
But why do you need two? That's the secret sauce.
Why do you need two? Oh, maybe because of the there's that you want it to be the same level, right? And then so to to compensate for that change in level, you need a PNP and an NPN common collector to kind of change it back to the original level that you want. You don't want that 0.7 VBE on decrease, basically, or increase, whatever it may be.
I agree with
What's another name for the common collector that would be appropriate here?
Level shifter, I think?
Yeah, exactly. Okay, here's a since we're here, my pen worked for about a third of the last class. So let's see if it's decided to work here. Nope. Okay, so we've got a current source here, and again, what's the square again?
you. Couldn't see your screen if you're trying to share it with us.
Oh.
Yeah, I don't.
How many times are you going to have to tell me that? Yeah. So yeah, you have a current source here, and what's this square mean?
Resistor.
Resistor. Yeah, okay. So what is a current source? What is that circuit that would replace the current source?
A current mirror.
A really big resistor.
Could be a really big resistor, and it could be a current mirror. Either one of them is perfect.
Okay.
So the current mirror that you did in the first lab and all was a single transistor. Looked like no pen. Looked like, whoops, I didn't know I was in red. And there's your current, and that would be this current right here. Okay, so that's this simple current mirror. How can you make even a better current mirror?
You want to active load it?
Okay, well that's what this is. This is basically a single transistor here. But you want to make it, when you change the voltage on that collector, you want the current not to change at all.
Change the voltage in the collector.
So here's kind of an unconnected question. If you change the voltage and the current doesn't change much, is that a big resistor or a little resistor?
If you change the voltage and the current doesn't change, yeah, it's a big resistor. Yeah.
Okay, so how can you make right here, if you're right here, what resistance do you see looking up?
RO.
RO, okay. So that's a big resistor, but how could you make it even a bigger resistor?
Put a PNP below it.
And then what's that called when there's two
Excuse me. And yeah. You cascode them.
Cascode. And then if you wanted a super duper awesome current source up there, what would you do?
Cascode the other side too.
The other side, actually, to bias it, probably is cascoded. But what's even a bigger, a way to get even a bigger R at this node right here?
Cascode the top one too.
It would just be, so this whole circuit is what goes there. I should have done that in a different color. So I agree, cascoding increases the resistance seen at this node. Is there a way to increase it even more over a cascoded?
Are you asking to add on to our cascode or something completely different?
It's the homework flavor number 4.
Gain boost?
Gain boost. Yeah, so you could gain boost it if you really wanted a good current source. Okay. So all of those are ways to make this look like a big resistor.
So when you cascode, are you replacing the transistor on the right? Is that what you're replacing that with a cascoded?
Yeah, the simplest biasing for cascoding. I just really wish my pen would work. Okay, pushing all the buttons in random order. Yay, okay. Turns out if you cascode the right, you need to have voltages for the bases of both of these transistors. So now this is cascoded. This node is this node, but you need to be able to give the bases the correct voltage. So you often have to do some biasing like that.
Okay.
So it's all about getting voltages for these two bases, for this base and this base.
So would you, sorry, I'm confused. Would you gain boost now that you've cascoded, or would you gain boost the one on the top?
This circuit right here is either this one. This is one option. This is another option.
Oh, okay.
And then this
I'm
is,
assuming, oh, sorry, the bottom one is the better option then? Is that what it's just?
well, it's more complicated. RO is a pretty good resistance.
Okay.
If RO is 100K, that means it's pretty darn good. If you need, a giga ohm, then it's super great, but RO might be just fine. In this case, you'll have a gain a little bit less than, just slightly less than 1. If you cascode this, then it will be like almost 1. So
Okay.
RO will give you 1, 9.9 something. Cascoding will be 0.999 gain instead of 0.995. And then if you use a resistor, then you have like 0.98 or 9.95 or something like that.
Okay. Sounds good. So then what do, I'm lost as to why we brought the current source in the first place. Is that you're saying that's a part of the stage?
Yeah, all of these circles right here need to be replaced with an actual circuit when they build, when they design the chip. They actually have to turn those into a circuit. And so now for the question. This is very Christmassy, red and green. Let's make it blue. So my question is, what's R in of Q10? Make that equal sign longer.
Oh, is it that like emitter degeneration, but instead it's the perceived resistance of the like it's R pi. It's the perceived resistance through the base at Q11.
Yeah, so it would be R pi Q10 times 1 R plus 1.
Ignore Q11 for now. Just pretend like that's a single stage. It's a really good question. I mean, that works, but then you have to cascade this, and it gets all messy. So ignore Q11 for right now. So, but what you said. So, what would the equation be?
Oh, it would just be R pi then.
R pi Q10. But what's the resistance below the emitter?
Is the resistance of that current source?
Exactly.
So would it be in parallel with RO?
What's the equation?
Oh yeah, it'll be okay.
The equation of a current mirror?
Of Rn for anything that has a resistance below the emitter. In this case, the emitter's up, so it's actually above the emitter.
It's that resistance times beta plus 1.
Yes, and you already said that this current source, if you just have a simple current mirror, it's RO. So you get, that's a lot. That's a really high Rn for Q10. What would that be if you used a cascoded current source instead of just a simple current source? We'll call this simple.
It'd be that like GM times like RO times, or it'd be the perceived resistance of a cascoded. It's like RO times R pi. I
Yes,
think.
yeah, exactly. And that would replace your RO right here, because the resistance looking into the collector of that compound transistor.
Mm-hmm.
So cascoded transistor is a compound transistor. That's GM RO R pi.
Okay. Good stuff.
It's a handy equation. Doing small signal analysis on this is yicky. Okay.
So then what about that Q11? If we just, how can we just ignore that though? Is that not a part of that stage then? Is that what we're assuming?
No, you can't really ignore it.
Oh, okay.
It just makes it too hard.
Oh, okay.
My kind of math. Oh, that makes it hard. Let's not do it.
Would it just not really affect the resistance all that much that we care? Or
It probably does in this case. Just I don't know what the Rn is here. If the Rn is much bigger than RO, then you can ignore the Rn of Q11. If it's less than RO, then maybe you actually ignore this and just use the R pi plus RE times 1 plus beta. But then now you have to decide if Q11 or Q12. So that's why I stopped.
Oh, so they're like in parallel then.
Yes.
Oh yeah, they are, because their nodes are connected. The both nodes are. Oh, okay, I see.
Yeah, be RO in parallel with Rn of Q11.
Oh, I see. Okay.
So another question, that current source is only 4 microamps for the common collector, the Q11 and current source common collector. Actually, I should start circling things. What color am I in right now? Blue. So we had this. Remember, for a stage, you want to go all the way up to the top voltage and down to the lowest voltage, rail to rail.
Mm-hmm.
And then we got this one. Okay, but there's only 4 microamps. Why might that be? You had 6 microamps on the diff pair, and you have 100 microamps on that next branch.
does it maybe just help to get your VBE voltage closer to like the Q11 VBE voltage?
That's an interesting idea. In this case, since there's a resistor below Q11, the resistor is going to wreak a little bit of havoc and be changing the current on there. So I don't think so on this design.
Are we not paying attention to the branch that Q11 is on right now? Is that like what we did last time? We're just ignoring that branch as well?
No, that's the next stage.
Oh, okay. Because
So,
I'm not seeing the current of that current mirror go down that same branch.
What you would do with this is you calculate the gain of each stage, and then you find the loading factor between each stage. And that's how you take into account that the Rn of Q11 is going to make the common collector that I just circled, make it not work exactly as you it would on its own. Okay. But yeah, you're right. But the loading factor helps you take care of that. Okay. But the 4 microamps.
Maybe because there is a high gain between with Q11 and Q12. So that you no, wait, I'm thinking.
Think a little bit more about this equation right here. And my pen's working again.
It's a function of current. So with really high current, you have really high Rn because of that 1 plus beta. Is that?
Well, beta won't change. If In changes, I out will change. So beta doesn't change.
So since R pi is beta VT over IC,
Oh,
a smaller IC will give you a bigger R pi.
Yes, exactly. So you already have a gigantorama Rn because of that current source. But on top of that, you just dropped your current. So now R pi is bigger. What about RO? What's RO?
Early voltage over
Okay.
the current. So that even gets bigger too.
Yes, and that's even multiplied by another 100 or 200. So dropping the current, if you want to protect against loading, that stage right there is just will be very good at not loading the diff pair. Okay, so it probably included that because the diff pair was getting loaded. And then they said, oops, I just shifted my voltage up. And then, as you said here, this stage right here is, I'm still in green. I thought I was in blue. Oh, well. Another common collector. Then that one just, yeah, probably just to shift it back down. No other function. Okay. So we're through 3 stages. And I don't know what I would call those 2 common collectors. I guess they're just intermediate stages. Just
Is it just for loading then? Is that why? So then there's no stage, but it's just a buffer stage basically to
yeah.
help for loading?
Yeah.
Okay.
Okay. And then what's the next stage you see? I'll change now.
That is a common emitter.
Okay. And what are all the pieces of it? What are all the pieces of that common emitter?
Yeah.
Source.
Okay, current source.
And I guess Q5 and Q7 and Q13.
Okay. Those aren't part of the gain state. That's my next question.
Okay.
What kind of stage is that? What kind of stage is the common emitter? Oh,
The gain.
yeah. I'm never good at keeping secrets. Okay. Yeah, so that's a common emitter. And when you see the current source, again, it's this circuit over here. And so what's up here is actually a PNP. So you've got NPN here and a PNP. So what flavor of common emitter is that?
You saying that the current source is a PNP?
Yeah, let's say it's a simple current source.
An active load.
Yeah.
Exactly, that's what it's going to be. So this is a CE with active load. Okay, so they needed some more gain, even though they're probably getting quite a bit of gain from this stage, just because of this little trick down here. But they wanted more gain. Okay, and now back to where we started. What's next? We'll go purple. I was just going to sit back and not say anything. I've kind of failed.
You're just having so much fun, aren't you?
Well, there's. Oh.
Go ahead.
Yeah. Oh, okay. I was just gonna say it's connected to what looks like another common Q13. I don't know if that's the very next part or it's Q7, but Q13 is common collector. And yeah, what were you gonna say, Casey?
Well, I was gonna say somewhere there. I think I could be wrong, but I think that somehow creates a push-pull output stage. I'm not exactly sure where to consider that to start, whether that's only Q6 and Q13 or if that includes all 4 of those.
Oh, okay. So, okay. Yeah, I wouldn't know where to go with.
Or actually, maybe Q7 and Q13. make up the output? Because Q5 and Q6 make a Darlington pair up there.
So that's perfect. One Darlington pair is equal to a single transistor.
Okay.
So then there's a single transistor up there, and then there's Q7 connected to a current source that's 50 microamps.
Oh yeah, currents. I think so. I think that Q5 and Q6 might be increasing the current from the 100 milliamps a lot, because you'll go into the base and then to the emitter, it'll be 1 plus beta more, and then it'll be 1 plus beta more after Q6. So I think you're providing a lot of current down that way. Maybe.
Yeah, I don't know. The only thing I can think of right now, we're looking at this, is that Q13 is used to decrease output resistance, and then now I don't know what else.
Okay, so if you drew a, I still have my pen. This is going good. This is a push-pull stage without. There's some stuff over here, but without that stuff, that's a push-pull stage.
To me, it looks like Q7 and Q13 make the push-pull. Oh, and I think with the push-pull, you need a 2 VBE on difference. So I wonder if the Darlington pair maybe creates that for Q13.
I think the Darlington pair is like the upper side of the push-pull. It's like the top resistor of the push-pull.
Or top transistor.
Transistor, excuse me.
Okay.
And it looks like Q7 and that resistor form that safety like we saw in the first one.
Okay. Actually, it goes all the way down here. For this particular one, the safety circuitry goes all the way down to the bottom.
So I'm confused by using that Darlington pair because it's going to increase your current a lot, and that resistor is there to, when it hits VBE on, the current goes the other way, or it reduces it, but isn't that kind of counteractive to have the Darlington pair and that safety feature?
Let me say it a different way. If current's needed, the Darlington pair can supply it. So it doesn't necessarily mean it's always conducting a lot.
Okay.
It means if somebody asks for it, it can give it to them.
Okay.
So which transistor is the bottom PNP here?
Q13.
Q13. So I do you agree that that's, oh no, we lost Raul. Do you agree that that's, the push-pull is probably made up of Q5, Q6, and Q13?
Yeah.
Okay. What else do you notice?
Their inputs are the same?
What's that?
Are their inputs the same?
Yeah, their inputs to the voltage at this node, at the base of Q13 and the base of Q5, they're the same. Why are they the same? That's a silly question, actually.
They come from the same place.
Yes, they're coming from the same node. They're basically connected with a wire. Do you remember? Let me go back to purple again. So this is our push-pull. The safety circuitry and the push-pull kind of overlap a little bit there. And do you remember how to figure out, so you said that the voltage here and the voltage here, so the base of Q5 and base of Q13, they're equal. But do you remember how to figure out what voltage you actually need to have the difference between those two base voltages? Do you remember how to figure that out?
So you would start at the input and then follow it down to ground and see how many VBEs you lose, or VBEs you drop, I guess.
Right idea, but you only have to go from the base of this, you go down 1, down 2, down 3. So you find the circle that encircles the push-pull, and inside that circle you're trying to find a path from the top base down to the bottom base. So the drop here is from the base of Q5 to its emitter is
1 VBE.
And then from Q6 to its emitter.
Another VBE.
And then from the emitter of Q13 down to its base.
1 more VBE, so it's 3 in total.
Yes. So it needs 3 VB but how many VB does it have between the two bases?
2? Or I'm
0,
not sure.
because they're the same?
They're the same. There's 0 VB drop, but you need 3. So what's this going to cause?
Issues.
I think we did the sound game last time.
Crossover travel, like crossover transconductance? No.
Over somebody started
distortion.
Yeah. So this right here, how it's drawn, that's going to have quite a bit of crossover distortion. And some of these schematics, they're going in the data sheet, and there could be a lot more circuitry actually in the chip, and they just want to make it easy for you to get the big picture of the circuit. So there might actually be something in the circuit that adds that 3 VB on. If you had a diode with the magic, basically if you diode connect a transistor, it gives you a VB on drop. So if you had to place something to get rid of the crossover distortion, what would you do?
Would you put one between the collector of Q12 and the base of Q13?
Collector of 12 right there, that would work. That would be 1.
And then you put 2 more in the same spot.
Yeah, you could put 3 right here. You could actually put, I can't really draw it here, but you could put 3 right there, or you could put 3 right here. Somehow you just have to separate the two bases by whatever voltage you had to travel from the base of the top one down to the base of the bottom one. Okay. Let's see now. So I guess I talked kind of slow today. Let's see, what can I... I'm not sure I can give you a very good introduction to frequency response in 2 minutes. But let me give you a big picture. Oh, how can I do that? No, I think I'll stop here, and then you all are actually synced with the other class. That's never happened before. Okay, and again, I'll post a few videos, hopefully not too long. And I have a handout that's like 1 sentence away from being finished that's on capacitance in transistors. So I'll post that. And then try to watch the videos before next Wednesday, and then we'll do some practice in class. Okay. Any other questions, comments? This is a pretty robust, professionally designed op amp. And now you can see that the blocks that we've been doing over the course of the quarter, those can be snapped together to give you a pretty powerful op amp circuit. Okay. Though I always keep talking after I say I'm done, but I think I'm done.
Sounds good. Thank you, Tina.
All right.
Thank you.
Thank you,
Later.
Professor.
Have a good rest of
Bye,
your day.
Raul. Yeah, you too. Have a good weekend.
Have a good one.
Raul, did you lose internet?
Yeah, I was losing internet throughout the lecture periodically. I apologize for that.
No, I'm sorry that you're having to deal with that.
That's okay. I'll watch the parts I missed.
Okay. Actually, I should